Hello everyone, and welcome to today's presentation. Today, I'm excited to talk to you about CT scans and how they work. We'll explore the basic principles behind CT imaging and its importance in medical diagnostics. So, let's get started and dive into the fascinating world of CT technology. Today, I want to talk about CT scans, which are a special type of X-ray tomography. Unlike regular X-rays, CT scans use a computer to create a detailed mathematical reconstruction of a specific plane or slice of the body. This allows us to see cross-sectional images with much greater detail. The technology behind CT scans was invented by Sir Godfrey Hounsfield, a physicist and engineer working for EMI Limited, a British company, back in 1973. Originally, it was called the EMI scanner and was mainly designed to study the head. You might also hear it called a CAT scan, which stands for Computed Axial Tomography. These scans have revolutionized medical imaging, providing us with detailed insight into the internal structures of the body that was not possible before. Computed tomography, or CT, is a powerful imaging modality that allows us to see inside the body in a very detailed way. What makes CT unique is its ability to create images of slices or sections of internal structures. This means we can view different parts of the body layer by layer. One of the key advantages of CT is that it eliminates the problem of superimposition, which we often encounter with traditional X-ray images. In other words, with CT, one structure doesn't hide or overlap another, so we get a much clearer and more accurate picture of what's going on inside. This capability is crucial for diagnosing a variety of conditions because it provides us with precise and detailed internal views. Overall, CT has revolutionized medical imaging by giving us this sectional, slice-by-slice perspective that enhances our ability to assess internal anatomy effectively. The basic principle behind computed tomography, or CT, is that we can reconstruct the internal structure of an object by analyzing multiple projections of it. Essentially, by taking various images from different angles, we gather enough information to piece together what's inside. This reconstruction relies heavily on the pattern of attenuation, which is how much the X-rays are weakened as they pass through the object. The key measurement here is the linear attenuation coefficient, often called mu or micro, which quantifies how dense or how much material is present at each point within the object. In practical terms, during a CT scan, an X-ray tube emits a fan-shaped beam of radiation. This beam passes through the body, and on the other side, a radiation detector assembly captures the transmitted X-rays. To get comprehensive data, both the X-ray source and the detectors are moved or rotated together on a carriage, scanning a specific plane of interest. This coordinated movement allows us to collect multiple projections from different angles, which are then used to reconstruct a detailed cross-sectional image of what's inside. This entire process exemplifies how the internal details of an object can be revealed non-invasively, highlighting the powerful combination of physics and engineering that makes CT a vital tool in medical imaging. Let's take a closer look at how the scanning process works. When the X-ray tube is fixed in a specific position, it emits a fan-shaped beam that passes through the patient. As this beam travels through the body, it gets attenuated depending on the tissues it encounters. On the other side, an array of detectors measures the intensity of the transmitted X-ray beam. Now, during a scan, multiple projections and measurements are taken from different angles, allowing us to gather comprehensive data about the internal structures. All these measurements are recorded by the computer, which then uses them to calculate the linear attenuation coefficients for various tissues. This data serves as the foundation for the reconstruction process, where the computer constructs a detailed image of the internal anatomy. The key idea here is that by analyzing how much the X-ray beam is weakened at each measurement point, we can accurately map out the different tissues inside the body. This principle underpins the entire imaging process, enabling us to generate high-resolution, cross-sectional images in a non-invasive way. Let's take a closer look at the working principle. Essentially, this slide explains how the system operates on a fundamental level. The key idea here is understanding the core mechanism that drives the entire process. What we're looking at is how the different components interact to achieve the desired outcome. Think of it as the backbone of the technology. It's what makes everything work smoothly and efficiently. By grasping the working principle, we can better appreciate how the system functions in real-world applications. This understanding also helps us see the connections between the design and the performance we observe. So, as we go through this, keep in mind how these fundamental concepts are the foundation for everything we've discussed so far. When we scan an object, the first key concept to understand is the field of view, or FOV. This is basically the diameter of the area we're examining during the scan. Think of it as the size of the window through which we're observing the object. Now, when we divide this scanned area into smaller parts, each part is called a pixel. These pixels are the basic elements that make up the image, much like the tiny dots on a digital screen. An important relationship to remember here is that pixel size is determined by dividing the field of view by the matrix size. So, if your FOV is large or your matrix size is small, each pixel becomes bigger, and vice versa. This impacts the resolution and detail of the image we get. Moving from 2 dimensions to 3, the volume element of the object is called a voxel. You can think of a voxel as a 3D pixel, representing a small cube within the scanned volume. The thickness of each slice in the scan corresponds to the height of this voxel, giving us a sense of the depth dimension. Understanding these concepts, FOV, pixel, and voxel, is fundamental because they directly influence image quality, resolution, and how accurately we can analyze the scanned object. They are the building blocks that help us interpret the data we gather during imaging, connecting to the overall theme of how imaging technology creates detailed, accurate representations of the internal structures we want to study. Now, let's look at how we calculate the linear attenuation of each individual voxel using measurements from multiple projections. Essentially, we start with this fundamental equation: n equals n0 times e to the minus micro x. This tells us that the detected signal n depends on the initial signal n0, the attenuation coefficient micro, and the path length x. When we have different projections, we get various equations like n1 equals n0 times e to the minus the sum of micro 1 and micro 2 times x. n2 equals n0 times e to the minus the sum of micro 3 and micro 4 times x. And similarly for n3 and n4, which involve different combinations of these micro values. The key idea here is that by measuring these different signals, we can solve for the individual micro values, which represent the attenuation properties of specific regions within the voxel. This approach is fundamental because it allows us to distinguish different materials or tissues based on their attenuation characteristics. And this is how multiple projections work together in the working principle. By combining these measurements, we can accurately reconstruct the internal structure with high precision. It's a clever way to interpret the data and get detailed insights into the composition of what we're imaging. Now, let's talk about how the attenuation coefficient of each voxel is expressed in Hounsfield units, or HU, which are also known as CT numbers. Essentially, each voxel gets assigned a CT number based on a simple relation. The formula is HU equals 1,000 times the difference between the voxel's attenuation coefficient and that of water, divided by the attenuation coefficient of water. To put it plainly, this helps us standardize the measurement across different tissues by comparing them to water, which serves as a reference point. Moving on, once we have these CT numbers, the image reconstruction process can be carried out using either Fourier transform, or FT, or filtered back projection, FBP. Both methods are crucial in creating the final image from the raw data. The reconstructed image is then displayed on a CRT or LCD monitor, and each shade of gray corresponds to specific CT numbers. This gradation of shades allows us to visualize different tissue densities very clearly. So, in summary, this slide highlights the importance of CT numbers in quantifying tissue attenuation, and how these numbers are used during the reconstruction process to produce detailed, interpretable images. This process is fundamental to the diagnostic power of CT imaging, making it possible to distinguish between various tissue types based on their attenuation properties. Just like in radiography, a CT image is also made up of shades of gray, ranging from white to black. This grayscale helps us differentiate various structures within the body. Hyperdense, or radiopaque, structures such as bones, calcifications, and acute bleeding appear white on the CT images because they strongly absorb the X-rays. On the other hand, hypodense, or radiolucent, structures like air-filled cavities in the lungs or bowel, fat, and fluid-filled spaces tend to appear black because they absorb fewer X-rays. Understanding these differences in appearance is key to interpreting CT scans accurately. It allows us to identify normal anatomy and detect abnormalities based on how different tissues and substances absorb radiation. This color coding, in a way, helps us visualize the internal structures clearly and makes diagnosis much more straightforward. Now let's take a closer look at the main components of a CT scanner. The first one is the gantry, which is essentially the large, donut-shaped part of the machine. This is where the magic happens, as it houses the X-ray tube and detectors that rotate around the patient to create detailed images. Next, we have the patient table, which is designed to comfortably position the patient and move smoothly through the gantry during the scan. Its precision and stability are crucial for obtaining accurate images. The operating console is where the technologist controls the entire scanning process. It allows for precise adjustments and monitoring, ensuring everything runs smoothly and safely. Then there's the computer, which is the brain of the operation. It processes the raw data collected during the scan to produce the detailed images we need for diagnosis. Connecting all these components is vital for the efficient functioning of the CT scanner, and understanding each part's role helps us appreciate how they work together to produce high-quality images. This interconnected system is what makes modern CT imaging so powerful and reliable in medical diagnostics. Thank you all so much for your time and attention today. I really appreciate your engagement and interest. This is the final slide, and I just want to leave you with a heartfelt thank you. Remember, the key points we've covered highlight the importance of understanding the core concepts and applying them effectively. Connecting these ideas to the overall theme, I hope you see how they can make a real difference in your work and initiatives. So again, thank you. I look forward to seeing how you all implement what we've discussed. Have a great day.